right, drift prediction. Let's start with some imports. Good, we can import things. Okay, so the first thing I want to do is generate every possible pair of chords. We're doing this for 4 key. And I'm going to do that with like a little trick here. I'm going to convert the binary numbers, or the numbers in binary to chords. Okay, there's the numbers. And then I believe it's :B04 for padding. Yeah. Okay. So there's my representation of the chords. I'm gonna need a map. I'm gonna need like to map to and from chords to. I'm gonna index them basically. Okay, so I to C. And then the backwards map. What did I do? Oh, enumerate. Okay, I have my chords and I have a map for them. So I'm going to populate a 2D array of the filling in the drift that we're supposed to predict. So I'm going to use D for the 2D array. And it's going to be, I'm going to use torch to populate, to like initialize it to zeros. Because that's just easier. It's one line, you know? Okay. But if I'm gonna figure out what the drift should be for any 2 pairs of chords, I need to know whether they're jacks or streams. So to do that, I'm going to make a function called hasOverlap. It's going to take in 2 chords and it's going to detect if there's an overlap with the lanes that are on. I guess is a way to explain it. Okay, so that if statement should represent if there's any overlap, basically. Like if we detect, we're going to iterate over each of the lanes. If both of them are 1s, that's what this means. If they're both 1s, that's an overlap. We return true. If none of them have an overlap, return false. Now drift is going to be conditional on hasOverlap. Why is this doing the squiggle? Huh? Did I? Oh, cool. I love that. I love that. That's a typo. So let's look at the question definition. Okay, so if it has an overlap, then that's jacks. Jacks is 100 milliseconds late. Late is positive. So that's going to be 100 milliseconds positive if hasOverlap is true. else minus 100. And let's see, hold on, let me double check that that's right. Yeah, that's how I did it before. I think that's right. Cool. So that's what the drift is going to be. And then we got to know what index we're putting the drift into in our 2D array. So that's where we use the C to I. Boom. Okay. Now D should consist of basically all the correct answers that we want the model to produce for each pair of chords. And to sort of see that, to visualize it, I'm going to use IAmShow. Awesome. Yes. That is a cool little pattern. This pattern is mostly the result of the way that we generated these chords using the binary numbers. But it is cool. And yeah, I recognize this. That means I did it right. Yay. Okay, so that's the Bigram model. Basically, D, given any two chords, is going to look up the drift for it. Congratulations, we have a statistical Bigram model for drift prediction for this problem. Now let's just train a neural net to produce that same 2D array. So the first thing I want to do is break this into X's and Y's. Okay, for C1 chords, so we're going to initialize X's and Y's. If I can type properly. So X's is going to be the two indices. And Y's is going to be the drift. Does that look right? Yeah, that makes sense to me. And then Y's is just the single dimensional array. And then I'm gonna turn these into tensors. And then ultimately we're going to be indexing into a 2D array. But let's create D, and we're going to initialize it to just some random numbers. That's the initialization of our model. I'm going to use a seed though, so that in theory you could get the same results at home if you ran this code. No, not 6. G. It's going to be 16 by 16, of course. And now we want to measure the loss. Okay, what's the loss between the prediction and the expected values? So first, we basically want to flatten D. There's a bunch of different ways you could do this. I think this is going off script, but I think you could do like view like this. Would that be like turn into a 1D array? Yeah, you could do that. That flattens it. But like that only works in this situation because we're doing every example once. So my inclination was to do something like this: :0. We're taking the X is this 2D thing, right? So I'm going to take the first element of every X example, and then I'm going to take the second element of every X example. And I think this is the same It's the same thing. But yeah, we get that, and that's the Y prediction. And then the loss, I'm going to use the mean squared error. So Y prediction minus Y's squared mean. Cool. And then we can just go ahead and set this up for the learning loop, right? So num epochs, the usual. Oh, I forgot one thing. D needs gradient, obviously. Right, we're using D for training. It needs to have a gradient. So how does this, we do d.grad is equal to none. We clear out the grads. Do the backward pass, then update. I think this is right. Yeah, data minus equals. Okay, we'll know that this works if we can train it, right? So like, you know, you can pump up the learning rate because it's such a simple problem. And this should go basically to 0. Yeah, okay. So we know we set it up properly. I'm just gonna reinitialize it real quick, and like just for demonstration purposes, I want to, you know, show the gradual improvement of the model. So we'll do show D, but this doesn't work because D is a tensor and matplotlib doesn't like tensors, so we're going to do toList. Okay. Yeah, so D starts out at noise. And, you know, this is like nothing up my sleeves. And then we're going to train it a little bit. And you can already kind of see the diagonal line in there. Nice. And this looks like it's basically already trained. I don't know, just train it a little bit more. But the specific values in D might not be right. Like this is just showing relative values. That's how the coloration works. But the values are way off, right? So that's why you the loss might the picture might look right, but the loss is high. So you just keep training it. So like, you know. And now it's totally trained, and now we can literally look at the values, and they look right. The two values we're looking for are negative 100 and positive 100, and these are very nearly that. So there you go. Simple problem, but solved it 2 ways.